Hi, I'm Patrick from 7bitwonders, and today we're solving the problem Farmer John's favorite operation from USACO 2025 January contest in the Silver Division. Before we start, today's main topics are prefix sums, the median and its properties, and the sliding window technique. So, this is all you should know in order to solve the problem. So, let's get at it. It is another cold and boring day on Farmer John's farm. To pass the time, Farmer John has invented a fun leisure activity involving performing operations on an integer array. Farmer John has an array A of n non-negative integers and an integer m. Then Fj will ask Bessie for an integer x. In one operation, Fj can pick an index I and subtract or add 1 to A of I. Fj's boredom value is the minimum number of operations he must perform so that A of I minus x is divisible by m for all I from 1 to n. Among all possible x, output Farmer John's minimum possible boredom value. So this is the problem statement. Okay, if we look at the example, we might be tempted at first, this is what I originally did, to apply modulo on these numbers and then using a greedy approach, try to find the minimum number of operations to make the number at index I for all I divisible by m. But this will not work, and this is due to the particular restrictions imposed by this condition. So before we even attempt at building an algorithm for this problem, we should understand what this condition actually means and how we can visualize it geometrically. So let's get to the drawing board. So this is the formula. A of I minus x is divisible by m for all I in that interval. We know from grade school we can rewrite this equation like this. A of I minus x will be equal to km, showing that it's a multiple of m by using this arbitrary constant. If we send x to the right hand side, we would get A of I is km plus x. Now, to actually get something meaningful out of this equation, let's apply modulo m to this entire thing. And we would have A of I is congruent to x, everything mod m. If you know where I'm going, this is enough to solve the problem. But if you don't understand how to visualize it on the geometric plane, then don't worry about it because we're going into detail right now. So, all I ask of you is to please forget everything we've talked about, cows, games, whatever, and let's consider this other problem. On a one-dimensional line, we choose 3 arbitrary points in which we put houses. These points are 1, 4, and 9. We want to build a supermarket such that the total number of steps each of the 3 people in the houses have to make to the supermarket is minimal. If such is the case, where should we put the supermarket on the one-dimensional line? Please, pause the video and have a go. If you've said the best point is the median of the 3 positions of the houses, then you would be correct. In cases where we have to calculate the minimum sum of the modulus A of I minus x, we have to set x to the median of the n values, or whatever many values we have. But why the median and not the mean? If we didn't have this modulus distance and we had squared distances or Euclidean distances, in that case, the mean would have been the correct answer. But for this exact case, we have to always use the median. If we look, this is basically how we write this sum for this example. If we set x to 4, basically if we build the supermarket on top of house number 4, we would have the best distance 8, which is the best we can do. you can try and play with many different numbers, but you're not going to get a distance less than 8. So we found out that the idea is to look at the median of these values. So this is our first hint to solving the problem. But this is not enough. And this is not enough because we can look back and see we have modulo m. So let's consider a modulo, right? Let's say 10. And we apply modulo on this one-dimensional line. Since we know the remainders always loop, so eventually you're going to start from 0 again. That means that all these numbers will go on this circle forever. This one-dimensional line, if we apply modulo, becomes a circle of circumference m. So you might have already guessed what changes from the original problem. Let's say we want to walk from point number 2 to point number 9. In the original example, you would have to walk 7 units, like this, one step at a time. You cannot go backwards because it makes no sense. But in this case, it's not optimal to walk from 2 to 3, 3 to 4, 5 to 6, and so on, as we could go to 1, to 0, to 9, which would give us exactly 3 points, 3 units, 3 steps. So this is how the problem changes. There is no set, path you have to go. You could go one way around the circle or the other way around the circle. This brings us to an important property. To walk from 2 points, the minimum number of steps you have to make is at most m divided by 2, or exactly half the circumference of the circle. So, there is also one more caveat we have to address. In the original example, if we wanted, to scan all the points, we have only one set beginning, that being at 1, right? But in this case, if we consider this line which loops to the beginning, but I wanted to make it a line to visualize it much more clearly, to walk through all the 5 points, we could go 1, 2, 3, 4, 5, or another valid way, because this is a circle and everything loops, we could go 3, 4, 5, we scan them first, and then we finish with the last two, 1 and 2. That means that we have to check n windows. Since we have n possible points, in this case 5, we will have 5 windows. So for n points, we have n windows to check the median, or basically the total number of steps after we find the median, to actually get the correct answer. And this is how the Farmer John's equation relates back to everything we've done until now. So this is the general gist of the problem. This is what it wants us to do, to look at all the n windows, find the median in all of these windows, calculate the distances to that median, find an answer, and among all of these answers, output the minimum. So, as we've discussed, we have to account for all n windows. Therefore, for the original array A, we need to extend it such that um, we have its continuation, just like in the example with the segment. So we do that by setting a of I is equal to a of I minus m plus m for all indices over n. This just means that for every number, we add the modulo, which is going to be that same number because adding modulo does not change the number. It just creates a copy which we will use in order to calculate the distances. To optimize time, we want to keep a prefix sum of the array such that after we find the median, we can find the left-hand side and right-hand side sums in O of 1 time complexity. So what do I mean by that? Well, as we've seen, we need to calculate some sums, and clearly we cannot iterate with a for loop in order to find them. So if we consider this example, we can use the formula that I wrote on the tablet, right? The sum of the modulus of the number minus the median element. In this case, I've accounted for the difference in size. So it will be this expression, right? We see that the median will reduce among all of these little pairs, and we'll be left with this difference, which if we look is the right-hand side sum minus the left-hand side sum. So the only logical conclusion we find is that the median does not matter, just the sums on the left and right. But why is this true? We know that if A3 is the median, then on its left and on its right, we're going to have floor of n divided by 2 elements. If we add a floor of n divided by 2 elements and subtract the same amount, the net change will be 0. So that's why it works. Now you might be thinking, this is an odd length array. Would it work for an even length one too? Yeah. And to prove it to yourself, I suggest that you write an example and do the exact same thing. You will see that the median element will be reduced with itself, and then basically the net change will become 0. In short, it's enough. So it's enough to write this expression to find the total distance from all of the elements to the median, which, as we've said, we're going to use a prefix sum to keep account of everything. So these are some implementation tips. Of course, I've seen other possibilities to write this formula. Additionally, how you calculate the left hand and right hand side may depend on how you've looked at the problem yourself or how you're familiar with manipulating indices. But in short, if you manage to do this, then it's enough. So without any further ado, let's write the actual code and solve this problem. All right, so we can write n, m, read them, n, m, and create our array A of size 2n plus 1 because I wanted to index it from 1. Now we can read the values, I plus plus. We read A of I, and since we want to go from the flat one-dimensional line to the modulo circle, we apply modulo to this array, modulo m. Good. Because we want to find the median, we need to have a sorted array. So we're going to say sort of A beginning plus 1, A begin plus n plus 1. So we sort all the elements in the interval 1n. And let's extend the array. N plus 1, 2 times n, I plus plus, A of I is equal to, or will be, A of I minus n plus m. Good. Now, let's find the prefix sums. 2n plus 1, and we initialize it with 0. I. Okay. Prefix of I is going to be prefix of I minus 1 plus A of I. And to find the answer, I'm going to set it to the max by 64. I'm going to find the median and divide it by 2. And for all n windows, we will calculate the left-hand and right-hand side sums. The left-hand side, I would say, will be prefix of median plus I minus 1 minus prefix of I minus 1. If these formulas look random, I strongly suggest that you take a piece of paper and a pen. Take this example, look at the indices, look where the median is, and by using prefix sums, I want you to understand how this formula came to be. Also, I want you to keep in mind that this I minus 1 is the uh, window offset, the sliding window offset. Because we have so many windows, we don't want to recalculate this. We just add an offset in order to make it correct for all the n windows. I64 right-hand side, I would say is n plus I minus 1 minus prefix of n minus median plus I minus 1. It's the same thing. You will find these formulas if you take an example and look at the indices, and you will see that these are correct. You may find different other formulas to calculate the left-hand, right-hand side, but I think this is the most straightforward and most elegant way to do it. Now, the answer, like I said, is going to be the minimum of the minimum distances. It's a mouthful, but that's true, of right-hand side minus left-hand side. And finally, we can output our answer. And to see that everything worked out fine, let's run the code. It passed, but let's see if it passes every test from the USACO checker. So let's check. And let's see if everything was all right. Thankfully, I'm seeing a streak of green, just like I like it. Good. So this was it for today's problem. Just as a recap, we've seen how to use prefix sums, the sliding window technique, and we've also worked with the median of an array. As some parting thoughts, I think this problem is pretty interesting, especially how from a single condition we've jumped from algebra to geometry. Basically, this problem made us jump a lot of hoops, but I think in the end it was definitely worth it. So, thank you for watching. Don't forget to leave in the comment section below your suggestions for what I should do in the next video. Like, subscribe, and I'll definitely see you in the next one. Bye!